Let's look at chaos. Some things can be predicted way in advance. For example, there will be a solar eclipse on August 11th, 9966, if indeed we're all still here. But some things cannot be predicted way in advance. Why are there no 21-day weather forecasts? Here's a 7-day forecast from Tom Skilling, famous weatherman here in Chicago. He's been on the air since I was a kid. But even the great Tom Skilling produces only a 7-day weather forecast. The Wikipedia page about Tom Skilling notes that he also predicted the 2011 Chicago blizzard in January, 2 weeks before it hit Chicago. Now, predicting weather 2 weeks in advance is impressive. Predicting eclipses 2 weeks in advance is not really so impressive. We can show mathematically why there are no 21-day weather forecasts. You may not see the connection between what we're doing here and weather forecasts, but we'll go over it in a moment. You'll see. Let's look at the equation y equals kx times 1 minus x for different values of k. For example, when k equals 2, we have y equals 2x times 1 minus x. We plug in a value of x, and whatever that output, we plug it back into the function. And we do it again and again and again. So let me show you what I mean. Let's take, for example, let's start with x equals 0.3. So we turn this on, press clear. Okay, 0.3, and press enter. And so if we want to enter this into the function 2x times 1 minus x, and then take that input and put it into the function again and again and again, here's what we do. So we have 2 times answer. Answer is second, and then the minus sign, the negative sign, times 1 minus answer. And here's what this is doing. When we do 2 times answer times 1 minus answer, and then press enter, it will take 2 times whatever the previous answer was, namely 0.3, times 1 minus whatever the previous answer was, namely 0.3, and calculate 0.42. Now here's the cool part. If we press enter, it will take 2 times our answer, which is 0.42, times 1 minus our answer, 0.42, and calculate that. And we just keep pressing enter. And notice what happens. We end up with 0.5. So let's try a different value of x, like x equals 0.1776, 1776. Type 1776. So again, let's type 1776, 0.1776, and then press enter. And now we're going to type in 2 times answer times 1 minus answer. And you'll see what we get. Whoops, not 4 minus answer, sorry, 1 minus answer. Whoops, sorry. Okay, and notice what happens. When we press enter, it just ends up at 0.5. So we get this sequence 0.1776, 0.2921, etc. And it just all leads us to 0.5. In fact, any value of x between 0 and 1, whether it's 0.3 or 0.1776, leads you to 0.5, which is called an attractor. An attractor is a number that the sequence zeroes in on. Now let's try k equals 3. We plug in a value of x, and whatever that output, we plug it back into the function. So instead of starting with 2x times 1 minus x, let's begin with 3x times 1 minus x. Again, we begin with 0.3, enter that, and now let's type in 3 times answer times 1 minus answer. Okay, and notice what happens. So instead of zeroing in on a number, these two alternate. They oscillate between 0.63 and 0.69. The numbers do not zero in on just one number like they do when k equals 2. Okay, now let's try k equals 3.5. And again, same story. So we type in 0.3. And now let's plug that into the function 3.5x times 1 minus x. So 3.5 times answer times 1 minus answer. notice what happens. The numbers get closer and closer to about 0.3828, 0.8269, 0.5008, and 0.8749. So they're oscillating among these four numbers. These are the four attractors. The numbers do not zero in on just one number like they do when k equals 2. They don't oscillate between two numbers like they did when k equals 3. They're oscillating among these four numbers. Now let's try k equals 4. Check this out. So again, start with 0.3, same as before. Enter. And now let's enter that into 4 times answer. Whoops, sorry. Answer times 1 minus answer. Okay, and press enter. And notice what happens. The numbers bounce around seemingly randomly. There are no attractors. The numbers do not zero in on just one number. They don't oscillate among 2 or 3 or 4 numbers. They just bounce around seemingly randomly, wildly. This is chaos. Chaos is deterministic behavior, which appears to be random. Here's what I mean by deterministic. If you do this exercise again with the same numbers, you're just going to get the same sequence of numbers. It may look random, but in a sense, it's not really random. It's predetermined. It's deterministic behavior, which appears to be random. This is what we call chaos. So when we do this, the 40th number in the sequence, if we start with 0.3, the 40th number in the sequence is going to be 0.7472. What would the 40th number in the sequence be if instead of x equals 0.3, we had started with x equals 0.301? Do you know what it would have been? 0.3706. Notice that if we start with something that's really close, again, when we start with 0.3, we get 0.7472. When we start with something close to 0.3, like 0.301, we don't get 0.7472. Instead, we get 0.3706. What if we had started with x equals 0.3001? Okay, that's pretty close too. How about that? No, we end up with 0.9400. How about this number, 0.30001? 0.4842. How about 0.300001? Now this number is really close. This number is really close to 0.3. So you might think, oh man, it's going to give us a number pretty close to 0.7472 once we reach the 40th number in the sequence. Well, it doesn't, 0.0293. How about this? 0.300001. What's the 40th number in the sequence going to be? Is it going to be anywhere near 0.7472? Not really. It turns out to be 0.9020. So notice, if we start with x equals 0.3, 0.7472 is the 40th number in the sequence. If we start with x equals 0.3000001, then 0.9020 is the 40th number in the sequence. A small change in initial conditions leads to a dramatic change in the outcome. By contrast with the previous equation, y equals 2x, 1 minus x, if we started with x equals 0.3, 0.4, 0.9, 0.1, 0.5 is the 40th number in the sequence. Changing the initial conditions generally has no effect on the outcome in the second scenario, but weather is like the first scenario and not like the second. Edward Lorenz discovered this in the early 1960s. He was a mathematician at MIT, Massachusetts Institute of Technology. He tried to predict weather based on temperature, air pressure, wind speed, etc. He ran calculations one day, and they did more calculations the next day, starting in the middle of the previous day's calculations. And here's what Lorenz obtained. The second day's calculations began to diverge from the first day's calculations right about over here. And then notice over here, by this time, they're completely different. Why? The computer stored data accurate to 6 decimal places, like 0.123456. But when he picked up where he had left off, he didn't bother to enter the 0.123456. He just entered data accurate to only 3 decimal places. So he basically got rid of all this stuff and just entered 0.123. And when you do that, you end up with a completely different answer. Accurate long-term weather forecasts are impossible because our measurement of important factors like temperature, wind speed, etc. are measured only so accurately. We don't measure wind speed accurate to 6 decimal places like this. We don't even measure it accurate to 3 decimal places. But if you lose those decimal places, you just end up with a completely different answer. So because our measurement of temperature and wind speed, etc., because it's not that accurate, because it's not accurate to 6 decimal places, there's no way that we can come up with an accurate 3-week weather forecast. If we're off just by a tiny bit, like if we enter this as the wind speed, when the wind speed is really this, we're going to get the wrong answer. This is an example of what Lawrence called the butterfly effect. A butterfly flapping its wings in Brazil could cause a tornado in Texas. The technical term for this is sensitivity to initial conditions. Weather is sensitive to initial conditions. A tiny change in temperature could have a dramatic impact on the weather. Not initially, but eventually. And that's why our weatherman, even the great Tom Skilling, does not go any further than a 7-day forecast.